and welcome back once again to the CERN Control Center. Today has been a very special day. We've entered new physics at 13 TV with stable beams colliding for the first time in the 4 LHC collision points at 10:40 this morning. We are here around the table with some of the protagonists of the day. As announced, we've collected questions through Twitter, and we can start this Q&A session together with Frédéric Baudry, Director for Accelerators. Giulia Papotti was the engineer in charge today at the LHC operations. We have Jan Uithoven from the machine coordination, and Massimo Giovannozzi. I wanted a theorist around the table with us because I know many of the questions are about interstellar physics style. I would like to start with you, Frédéric. Can you give us a summary of how the morning went?
I will not give the summary. I will leave for the people who are acting on the machine. I just want to say it's an emotional moment. It's a great moment, achievement, a good achievement. I want to say that we stopped physics the 16th of February 2013. It seems a long time ago, and we had almost 2 years of long shutdown with a lot of job in the tunnel. After that, we have to qualify the machine with a long powering test to be sure that the machine could go up to 13 TV in terms of a magnet, in terms of protection. And we inject the beam, do you remember the Sunday Easter? And after that, we said 2 months, and just 2 months after that, we have beam in the machine in physics. And for me, it is really a great achievement, a great work for a lot of people. And this, I have to say, today my heart
Your heart is beating.
Yeah, it's good. I'm very happy of that, and I think it was good. For the job of the morning, I think I was assisting to all, but I prefer to give the floor to Giulia or to Jan, because they were in charge of the machine, and I think it's their role. I think it's better to have Giulia.
Let's have Giulia first, who was driving the machine for the morning. It was a tough job today.
Yeah, we can say it's easier to work when there's less people watching, like not the whole world watching. I like that better, but never mind. Overnight, the last checks for making sure that all the machine protection elements are in place and acting correctly were done. So when I came on shift at 6:45 this morning, that was done, and we were ready to start injecting for stable beams for physics. We had a couple of issues to start with, so we couldn't get beam from the injectors. We had another issue on our side. Something broke overnight. Once those two things were fixed, we went for the first injections, the first ramp. Unfortunately, we lost the beam to an interlock, so we had to try again. That often happens. We can also say that maybe it was good that we could keep the suspense going for just another couple of hours.
Of course, for a live event, that's what you need. You need a couple of...
Exactly.
But in the end, you proved to be the best crew for the best ship, as Sergio Bertolucci said in his quote. He's a sailor, of course. Jan, you were at the machine coordination, and you were leading the meeting this morning. How did you feel?
Okay, you had hoped, of course, that we could say everything is fine with stable beams and so on, but it was like it is in reality. Yeah, so you can have a beautiful plan. As machine coordination, you make your nice plans over certain days, and you have foreseen to go for stable beams and for physics. We had foreseen to do that this morning to be ready just before the meeting, and in the end, it is like in real life. You had some things that needed to be fixed, and it happened a bit later, so you had to adapt your planning. And that's the way it is. But in the end, it was great.
And now that the beams are colliding, the experiments are taking data. We have the 4 experiments in remote connection with us still. We have LHCb, ALICE, ATLAS, and CMS. If any of those is ready for questions, we could start with the first question from Twitter, which is exactly about the physics at 13 TV. So it's a question for one of the experiments. Who is ready, Steve?
It looks like they're all ready. Who do you want to go to? How about CMS first?
CMS. So
okay.
Who we have at CMS?
So,
hello.
We're going to Atlas. Okay. Who is at Atlas? Alex or Ludo?
No, it's Rob McPherson.
Rob McPherson. We weren't expecting you. Okay. So, Rob, the first question we get from Twitter is, what's the difference between this and the 13 TV collision that took place some time ago?
You mean the earlier collisions this year?
Earlier collisions where we broke the energy record.
Yes, but now the LHC's declared stable beams, as they call it, which means that we can be confident that the beams are running smoothly and stably and will not damage the detector if we turn it on to full voltage. So what we've done now is turned on all of our detector systems, which we will only do with stable beams declared, which happened today. So now we're really able to take physics data with all of our detector running, and that's the first time ever, just an hour or so ago.
Thank you. And the next question is, what new particles are you hoping to find at the 13 TeV threshold? Who wants to take that? We ask Atlas first. It's a question for the four of you, actually.
Yeah.
So let's start with Atlas.
I mean, to me, the biggest unanswered questions following the discovery of the Higgs is what's behind the Higgs, and possibly is that related to dark matter? So it's the new particle searches that we're going to be doing later during this year and then for the next two years of runs. And I really hope we'll see a signature that has significant missing energy, which is a sign of dark matter particles being produced in the LHC. Perhaps that ties into the astronomical measurements of the missing matter in the universe that we don't quite understand. That takes some months or years of data. This is the first day.
Thank you, Rob. That was Rob McPherson from Atlas. Can we now move on to CMS? And I'd rather ask the same question to CMS. What new particles is CMS hoping to find at 13 TeV?
Hello. So I think CMS hopes to find the same things as Atlas and as any other experiment. So in principle, of course, dark matter, anything related to the dark sector is a high priority, but also we shouldn't forget the supersymmetry. So during the run 1, we did a lot of searches for supersymmetric particles, but so far we haven't found anything. And run 2 may be the moment to either finally find some SUSE signal or discard the possibility of SUSE.
Thank you, Rebecca. In the meantime, your spokesperson, CMS spokesperson, Tiziano Camporesi, has joined us at the table. You were quite far away at 0.5, and you managed to come at the speed of light through the tunnel?
No. I came to bring a significant token of recognition.
Yes. And since you're here, I'll ask you the next question, because they answered quite well, I guess, Rebecca and Atlas and Rob McPherson. So what are the expected extra details from the Higgs predicted to be over the basic signal of the Higgs that you already detected? Are you keeping studying the Higgs, and what's the advantage of studying the Higgs at 13 TeV?
Absolutely. I mean, studying the Higgs at 13 TeV means that we produce more Higgs to start with. Now we know where it is, we can actually look for it in details, and the details means that we're going to improve, if you like, we need still to fully describe the identity card of the Higgs. And so far, if you like, we have a fuzzy picture of the Higgs, and the data at 13 TeV, and all of the luminosity which we will collect in the next runs, I mean, for over the next 10 or 15 years, are going to help us getting a much sharper picture of the Higgs. Now, getting a sharper picture of the Higgs will also allow us to tell whether there is any difference from the predicted picture of the Higgs, and which would be an indication, for example, of seeing something which is new and unexpected and beyond what we call beyond the standard model.
Thank you, Tiziano. I guess the next question is for our theorist, Massimo Giovannini. Somebody asking about the graviton. How likely are these new 13 TeV collisions are to give us clues about the existence of these phantomatic particles, the gravitons?
Well, I guess that the first run of LHC established the interesting conclusion that gravity is basically the one we knew, that doesn't get particularly strong at the scale of the TeV. So the gravitons people wanted to see were, as they called them, extra-dimensional gravitons, which are not the ones we hope to see actually with the second run of LHC. The usual graviton, more likely, the one predicted by general relativity, will be seen by different devices like typically interferometers, wideband interferometers like LIGO in the United States or Virgo in Italy. And, for what concerns the gravity we understand today, I think that, LHC cannot, tell anything, right, concerning the any test or existence of gravitons.
Thank you, Massimo. Questions about the machine. I guess it's for Frederic. Why did you change from the design energy of 14 TeV to the present energy of 13 TeV?
Good point. The machine is designed for 14 TeV, that is 7 TeV per beam. During the long shutdown, we prepare all to go to 7 TeV, but we took the decision to limit the energy to put as soon as possible the beam in the machine. Okay, we try to explain. The main thing is what we call the training of the magnets. A superconducting magnet needs some training to reach a nominal field. Then we had some simulation that saying that we will need around the machine what we call a quench, transition to resistive, 150. And this is taking some time. And to go to 7 TeV, we know that we will need, let me say, around 1,000 quenches. Then it was a decision to do a powering test and to reach in 3 or 4 months this 6.5 TeV, to give physics at 13 TeV in the machine, to look at during 1 or 2 years what is the behavior of the magnet quench with beam, and after that to take a decision. That now what we want to do is to analyze the campaign we did for the quenches. We did, by the way, 172 quenches. And our prevision was 150, and you can see it's slightly above. Now we want to study all these quenches, and also now we want to see the behavior of the magnet with beam during the at least 15, and with our colleagues for experiment, we will have to decide, do we want to increase slightly the energy, and what is the compromise between the time to do that and the 6. That is, for me, it was a good thing to restart physics as soon as possible, to have physics, and maybe later during the run 2 or maybe run 3 to increase the energy.
There's another machine question for Julia. Somebody wants to know, James Hagerman, wants to know, how do you dump the beams, and what does it really mean, dumping the beams?
So the beam at the LHC, once it's at high energy, it's so powerful, it has such a big energy that there's only one safe place to put it. So we need to make sure that we extract it to what is called the beam dump, which is in 0.6. I'm sure Jan can add words to that. What we need to make sure also is that if anything goes wrong on the machine equipment, then the first thing we do is extract the beam onto the dump, and then all the rest can fall apart. Say that the current in a magnet changes because, like, I don't know, a thunderstorm has come close by. We first extract the beam, and then the current can change and drift slowly. So Jan is one of the experts for the beam dump, so I'm sure he's happy to chip in some words.
The beam or dumping the beam means there is our magnets which have a rise time of the magnetic field which is very fast. Yeah, so within 3 microseconds the field goes up to maximum, and then it goes down to a tunnel of about 1 kilometer long, and at the end there's a big beam dump block at which it's dumped. So extracting is the beam dump, and this is a very fast switching magnet which you switch on.
We now have a question for the LHCb experiment. LHCb, are you following us? Are you there?
Yes, with great interest.
Okay, hi Guy. So, what are the most promising channels for finding physics beyond the standard model? Which one will you be focusing on at this energy range?
Oh, well, we are looking at a variety of decays of beauty particles, but many of which are very, very rare. So, for example, a decay of the B meson into 2 muons, which was we first saw evidence of and indeed observed with the run1 data. We want to study that in much more detail and measure its the exact rate in which at which it happens, because the exact rate needs to be measured and compared to the theoretical prediction to understand whether what we have is compatible with the standard model or in the direction hinted at by new physics.
Thank you, Guy. Another machine question. whoever of the three of you wants to take it, how is the beam controlled so as to collide at each detector? Why does it not collide all around the beam path, 27 kilometers? Who wants to take that? Julia?
So one thing that we do is, okay, the beam is not continuous, but it comes in bunches, so it's only discrete packets. That's the first point. We need to make sure that we put these packets at the correct longitudinal location in the ring. So instead of through the 27 kilometers, we put it only at definite locations. The next thing we need to make sure of is that the protons that are running around in ring 1 meet the ones that are running around in ring 2. And so we need a synchronization between the two rings, and that we call the cogging. So we're really shifting, mostly at the beginning of the run, and then it's okay, but we're really shifting one ring with respect to the other one so that the beams meet only at the center of the experiment.
We now have a physics question. We would like to ask it to Atlas. What is the highest possible mass of a particle that could be produced in the LHC at 13 TeV? Atlas, what's your answer?
So the absolute theoretical maximum would be 6.5 TeV. Now, we can't get there for a while because protons are not point particles. They don't each, when they collide, release the full beam energy. What instead happens is a bit of a proton, let's say a gluon, hits another bit from the other proton, which is also perhaps a gluon, and then those two gluons only carry part of the proton in energy each, and then they release that fraction of the proton energy when they collide. So normally, after perhaps a few months of data taking, we'll be probing the TeV scale. Perhaps not that much for processes that don't happen very often, have what we call a small cross-section. And then later, as we get more and more data, we'll be pushing well above the TeV scale.
Let me ask the same question to CMS. Tiziano, before you go, what's your take on that?
Well, I agree with Rob because basically...
You better.
No. On the other hand, I think that in practical terms, very likely we will be reaching in the not too distant future order of 3 to 4 TeV, and it will take the full program before we really reach the ultimate possibility. So
what's the view of a theorist on these supermassive particles?
Well, I think that CMS explained it very well. I think that there is an intrinsic limitation due to the energy of the colliding beams. So I think that in the best of all possible cases you would get to up to 6.5 TeV, but this is actually not possible in practice because of the internal structure of the proton, because the proton is not a point-like particle, like for instance the electron. So
okay, Steve is telling me that CMS is going to leave soon, so let's ask another question to CMS. What else has been found beside the Higgs boson?
Hello.
In the first run.
In the first run.
Right.
We actually were able to find many things. So we rediscovered the standard model, seeing basically all the processes that we have seen before. But then many new processes that we were anyway expecting could be accessible with the energy and data for run 1. So for example, we could cover a couple of the single top processes that have never been observed before the LHC, and many other standard models that require a little bit more data or center of mass energy. So of course, apart from the things that we have seen, we have probed a lot of phase space for things that we have not yet seen. So let's say that during run 1, we explore as much as we could the phase space that was open for us.
And
so there were a lot of things.
Thank you, Rebecca. That leads me naturally to a question to Dave Charlton. Atlas spokesperson has just joined the table. What is the short list of what's next at 13 TV for Atlas?
Yes, you can
Yes,
start.
yes,
Yeah.
go ahead.
Well, to start with, of course, we are ramping up the luminosity, seeing more and more collisions taking place, and we're getting the detector fully recommissioned. I mean, we've done a lot already so far, but we have a lot more to do. Really to get the detector back to tip-top peak performance, and so we're collecting a lot of data, and then we will look, first of all, we'll do as we did in run1, we will look for the processes that we know about and re-establish those. We'll re-establish production of Higgs bosons in the new data. And then, or at the same time, we'll also be looking for possible new physics processes which may be happening. I expect you've talked about some of those already, whether looking to see if we see signs of things like dark matter or perhaps extra dimensions of space and time, other new particles showing up. And there's really a very, very big menu of different things we'll be looking for with this year's data and the subsequent year's data.
It's a very big program indeed. We have Alice, the Alice control room, talking to us right now. Hello, Alice. Can you hear us?
Yes, we can hear you.
Okay, hi. So, what's the to-do list for Alice now that you've got 13 TV collisions?
So, yeah, the to-do list is now, of course, to get the detector fully up and running. We had a very long commissioning period already in the last 3 months. And behind me, people are very excited to see the new collisions, to see data coming in. So what Alice will do now in the next months is to take data with proton collisions as the others. And we are gearing up to the end of the year where we will have heavy ion collisions, because the main physics of Alice is in heavy ion collisions, where we we look at nuclear matter at temperatures, highest temperatures that have been ever achieved, and in order to reproduce like the state of matter, like it was in the very early universe. And this is what we'll do again in the end of the year during heavy ion collisions that will run for about 1 month in November of this year.
Thank you. Thank you very much, Alice. We have a question regarding safety from Cara Livesea. What safety features are in place to prevent geological instability being triggered by the CERN experiments? Frederic, would you like to take that? Geological instability. We know the machine is very sensitive.
Okay. What is the effect of the movement? Okay, it's true. The machine is very sensitive because the machine can correct the orbit of the machine due to the tide, the territorial tide, and the machine is so high precision that we can see any movement of the ground, and we are correcting the orbit to follow the tide. After that, we can. I know that we can detect a lot of things. I think when we have an earthquake around the Earth, we can detect, but it's not big impact on things. We can detect because the machine is very, 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 very precise. But I didn't understand very quick.
The safety.
The safety. What is safety? I say for us, the machine was installed on the special rocks, what is solid and so on. Then it's very stable. Every year with the orbit continuously looking the movement, and every year we are looking by survey where is the machine.
But
we
this movement
is
do
very
not
slow.
pose any danger, any threat to the
No, because the
stability
movement,
of
we
the
have
Earth.
some movement, especially in one point of the machine, but we are speaking millimeter over years, and it's not a big deal. I think from LEP we have 1 centimeter we can correct, but it's a very slow movement of millimeter per year, and I think no problem. We can detect the movement of the Earth, but
yes.
the place was chosen for that to have a stable thing.
Exactly. We are in solid rock.
No problem.
100 meters below
No problem
ground.
at all of safety, and we can correct all the movement of the Earth for the machine.
I have a general questions about the experiments. Maybe Dave, you want to take that? What are the functional differences between the 4 experiments?
Okay, so 2 of the experiments, the 2 biggest experiments, Atlas and CMS, are quite similar to each other in terms of the physics that they're trying to do. The other 2 experiments, the other 2 big experiments, which are ALICE and LHCb, they are focused on particular types of physics, particular areas of physics. And so, as we heard, ALICE is particularly focused more towards the heavy ion data taking that comes later in the year. And LHCb is looking in the very forward regions, in a particular angular region, and is looking particularly at B hadrons, B particles, beauty particles that are produced in decays. In Atlas and CMS, the physics goals are very similar, but the technologies we use have evolved differently in the two experiments. And so in detail, we have different technologies. CMS has a very large central magnet, and Atlas has a more complex system of multiple magnets, for example, and we have different technologies for the particle detectors, the calorimeters, and so on. So in detail, there's a lot of differences, but in principle, what we're trying to do in Atlas and CMS is the same type of physics.
Thank you, Dave. Yes, one more question for CMS. We can share that with our theorist. First to CMS. As experimentalists, which predictions by theorists does everybody like best? Are you hoping for supersymmetry, extra dimensions, dark matter? This is from Reddit. Ask a chemical engineer.
So I think SUSY supersymmetry is probably one of the favorites at the moment. Of course, dark matter is one of the main goals of the searches in run2. But SUSY is what everybody is kind of hoping for, because it will mean a lot of new particles to discover and to study.
Thank you, Rebecca from CMS. So, Massimo, what are the specific theories and models that you think LHC at 13 TeV or even at 14 TeV has the capacity to confirm or rule out?
Well, I think that this is really $1 million question as far as the will is concerned, because we would like to discover as much as possible, but at the same time, it's true that the theoretical community in the past years has been very much biased towards supersymmetry, and so certainly we will be able to learn something about that. But I would like to mention something that I think Sergio Bertolucci said once during a talk, talking about stuff that has been done at CERN in the past, namely when it was the time of the ISR, which was a machine. One of the first machines at CERN. At that time, people were actually looking forward, looking at the forward physics, looking at the expanding proton, at the expanding cross-section of the proton. So the idea was that the proton was expanding at high energies. So theorists at that time said, look forward, and Sergio said if people would have looked a little bit around, probably they would have found some J psi, for instance.
Already at the ISR.
What I would suggest to experimentalists as a theorist is that they should not go in one direction only. They should look around and probably also, have an unbiased picture of what's going on, and probably, this, of course, is not that I'm suggesting a specific experimental strategy, but, of course, so, minimum bias events are very important, and, unbiased views are very important.
Thank you, Massimo. Another question for Jan about the machine. Is it true that it would take 1 year to train the magnets to go from 13 TeV to 14 TeV?
It's of that order. I think it's a question which Freddy answered in the beginning. It was basically the answer, why are we now having 13 TeV collisions and not 14? You had about 150 training quenches, 172, so it's all of that order of time if you can do this efficiently.
Okay, it's difficult. Okay, it's true that to recover for one quench, when your magnet is quenching at 7 TeV, more or less is 10 hours. And you have to recover, you have to re-put all the conditions, to do new ramps, and the best thing you can do in one sector, 2 quench per day. And after that, you have to multiply to do 1,000. But it's not only the time. You have to look at all the... A quench is a very severe shock for magnets. And to do a lot of quench on magnet, you are also the lifetime of the machine. You have to look at it very carefully. Then it's the time. Definitely, we will need, let me say, between 7 months to 9 months to do all the things at a full speed. But a quench, as I said, we have the quench heater, the glue on the magnet and so on. We want to look at the things and not to damage the machine if we have to to remove. You have one magnet, you are having a problem. You are losing 2 months and a half for the machine. Then it's a kind of thing. Then once again, is more or less we want to learn what we did to try to improve the thing, maybe to parallelize more the things, and I hope later we will be in a position to give more precise time and to minimize the risk to do this campaign.
And the next connected question, these were questions by the way from Physics World, is quenching the only barrier at 14 TeV?
No, it's not the quench. It's the design. The magnet was designed. All the magnet, all the powering of the LHC was designed for 14 TeV. To say the magnet, the current leads, the power converter, all was designed for 14 TeV. And to go above, we have a little. Oh, by the way, now it was 14 TeV plus 10%. We have some more thing. But let's say to start with 13 TeV, to have physics, to look at where is the physics, and after that we can think how to increase to 14 TeV towards 14 TeV. What I said is a compromise. For me, what is important is not only the peak luminosity, but the integrated luminosity. I think for experiment, what is very important. Then the time is important, the quality of the beam. If you are at 14 TeV, but every run you are losing, you are quenching and losing time, it's not efficient. Then we have to learn.
It's a compromise.
It's a compromise, and for that, I think it was not a comfortable zone. When we choose to run at 13 TeV, people said, "Okay, it's a comfort zone." No, we demonstrate that we did 172. Primary quench, more than 600 secondary quenches with spoke times, and now we have to learn. We are just at the start. I want to see the machine, the behavior of the machine with a higher number of bunches, higher intensity. I want to see that. I want to see the experiments with high pile up and so on. And next year we will think again. And I think we have not to jump one goal to another goal.
We have LHCb and Atlas, the control rooms, ready to talk to us. So, who is there? Who wants to talk first? Say hi.
Hello? Yeah, can you hear? This is Atlas.
Okay. So, yeah, there's a strange question, but maybe you can answer that. There are some of the people who are tweeting, they're asking whether there is the possibility of colliding other particles but protons, for example, muons. Would you see muons colliding in the middle of Atlas?
Not in the LHC, which is a proton or heavy ion collider. It's a hadron collider, so we can collide protons against each other, heavy ions like lead or gold against each other, protons with lead. There are special dedicated R&D projects to perhaps build a muon collider some long time down the road, but not in the LHC.
Thank you very much. What about extra dimensions? Would you hope to see them at this energy range?
Well, so we have another step now in energy and our energy reach, and that will increase our sensitivity to extra dimensions, perhaps at a higher energy scale, which means a smaller distance scale. We have not seen any signs of them so far, but should they start to emerge, and this relates to the graviton question very directly that was asked earlier, then yes, there is a new window of opportunity in terms of energy scales or short distance scales now with the 13 TeV data once we have a sufficient amount of data. Actually, some extra dimension signatures are some of the very first signatures that we could potentially see with the new data. It can take very little data actually with the higher energy.
There's another very interesting question, maybe for you, and a comment by Thierry. Will this open the search to the fourth generation of particles? Are we on the verge of looking into that?
Well, if I continue from Atlas,
yes,
the fourth generation, it's an interesting question. One thing we know about a fourth generation would be that if it has neutrinos, they must be greater than about 45 GeV. We learned that from LEP, the previous accelerator in the same tunnel as the LHC, the Large Electron Positron Collider. Could there be heavier particles like our standard model particles? Absolutely, we search for them. They're not theoretically favored, but what's interesting is sometimes they give unique and different experimental signatures, even if not in a theoretically favored model of new physics, but we nevertheless look for these experimental signatures and perhaps use fourth generation as a motivation. And I think that fits in very well with the sentiments expressed earlier that we want to search for everything. Sometimes we find a model theorists don't like, but it gives a different signature, so we go search for that. Sometimes it's a favored model, like supersymmetry, and we search for that. And then we also have more general analyses to look for anything beyond the standard model. For fourth generation, as you could ask for my theory colleague, it's not a favored model particularly, but we nevertheless do search for it.
Thank you very much. Now we have LHCb again with us. Are you there?
Yes, we're here.
Hi, guys.
Hi.
So, question for you. Does LHCb look at anything else than beauty quarks?
Absolutely.
And what do you look at?
That is our name. So as well as beauty quarks, we look at charm quarks. That's a slightly lighter sister of the beauty quark, but no less interesting. And these are produced in even greater profusion. But then in addition, we look at the heavier particles which Atlas and CMS study. For instance, the W and the Z bosons, the top quark. This morning we published using run1 data our first observation of the top quark in our unique region of coverage, which is forward close to the beamline. So there's many studies we can do of particles other than beauty and charm, but what is unique to us is the coverage, our forward acceptance, which means we are detecting particles which are emitted rather close to the beam direction.
Thank you very much. I think we can close this Q&A session. We've been going on for quite a while. The morning has been heavy. Is there Alice? There's Alice on?
Yes, we're here.
Hi.
Hi.
Yes, so you're more looking for the quark and gluon plasma, and does the 13 TeV threshold make any difference for you compared to the 14 TeV session, which is the nominal energy that the LHC is going to reach?
So a difference in energy, of course, is equivalent to a difference in pressure or in temperature, if you want. But this is not such an enormous difference. So 13 to 14 TeV is not making a big difference for ALICE. The important new thing that we have in ALICE is that after this long shutdown, during this long shutdown, we installed a lot of new detector features that increase the performance of the detector, so we can have a much closer look now at the heavy ion collisions. So, as I said before, we are starting up this machinery, and we really can do now precision measurements of the quark-gluon plasma in this run2.
Thank you very much. I would like to now thank everybody around the table before closing this session. It was quite an exciting morning, quite a tiring morning, especially for you, Giulia. So I would like to thank you first of all. Thank you, Giulia Papotti, engineer in charge in shift today. Is your shift over? You're finishing at 3 in the afternoon. Thank you, Frédéric Baudry, for joining us, Director for Accelerators. It was a big day for you too. Your heart has been beating all the way through. I would like to thank the two spokespersons who joined us and have just left, Dave Charlton from Atlas and Tiziano Camporesi from CMS. I would like to thank the control rooms, Atlas, LHCb, CMS and Alice, who've been very patiently answering the questions from our Twitter followers. Thank you, Massimo Giovannini, our theorist in shift today. Thank you, Jan Outhoven, for the machine, the LHC machine operations. Thank you, Steve. And thanks to the technical team. And I hope to see you soon for a new milestone. I hope it's going to be a new discovery. And good luck, LHC. Bye-bye.
C'est une théorie qui marche très bien, qui a eu 30 ans de succès en physique des particules.
We know that it's an incomplete theory.
Pues me imagino que en el run2 nos van a esperar muchas sorpresas.
Le evidenze di nuove particelle.
Materia, która nazywa się plazmą kwarkowo-gluoną.
The mystery of dark matter.
To access the other parts of the puzzle.
Zou dat fantastisch zijn, want het is gewoon een nieuwe fase in de fysica.
It will help to explain this great puzzle about the universe as a whole.
Follow physicists at CERN on their journey towards new physics.